Modern technology is centered around speed and mass production. With computer-aided designs, artificial intelligence-driven automation, and global supply chains, it undoubtedly makes our lives more convenient. Yet, quite surprisingly, many ancient technologies are considered superior to contemporary ones in terms of both durability and functionality. Archaeological evidence shows that certain methods used in antiquity have withstood thousands of years, surviving natural disasters, climate fluctuations, and the erosion of time. In stark contrast, much of what we manufacture today loses its function within a few decades, often requiring constant maintenance or replacement. This paradox raises a fundamental question. Why do ancient technologies often appear more resilient and effective than those we use today? The answer lies not only in material science but also in the socio-economic structures, production philosophies, and cultural values of the time. Where antiquity emphasized longevity and endurance, modern industry often prioritizes rapid consumption and cost efficiency. Thus, the perceived superiority of ancient methods does not emerge solely from technical knowledge but also from a fundamentally different worldview and definition of necessity. 1. Material durability and longevity. When we examine the technological devices and machines of the past, one of the most striking features that emerges is their exceptional durability. Unlike many of today's products, older technologies were often built to last for decades, sometimes even generations. From the sturdy mechanical watches passed down within families to the robust cast-iron stoves and heavy-duty rotary telephones, the longevity of older technologies reflected not only engineering practices but also cultural and economic values that prioritized permanence over disposability. The contrast with contemporary consumer goods, which frequently fail after only a few years of use, raises important questions about how materials, design philosophy, and industrial practices have shifted over time. A major factor contributing to the resilience of older technologies lies in the choice of materials. Earlier manufacturing processes favored metals such as steel, iron, copper, and brass, as well as natural materials like wood and leather, all of which were capable of withstanding wear and tear. For instance, radios and televisions built in the mid-20th century often used solid wooden casings and heavy glass tubes. These were not only more resistant to physical damage but also easier to repair and replace when individual components failed. By contrast, modern equivalents rely heavily on plastics and lightweight alloys designed for mass production and cost efficiency. While these materials allow for portability and reduce manufacturing costs, they often degrade faster, warp under heat, and break more easily. The difference in material choice reflects a transition from durability to affordability, signaling a profound cultural shift in how technology is valued. Another dimension of longevity relates to repairability. Older devices were typically modular, meaning that when a part broke, it could be replaced or repaired without discarding the entire system. For example, mechanical typewriters and sewing machines were engineered with accessible screws, gears, and springs that any skilled technician or even a knowledgeable user could fix with relative ease. In contrast, many modern products are intentionally sealed, glued, or soldered in ways that discourage repair. Smartphones, laptops, and home appliances often require specialized tools, software locks, or even void warranty clauses when opened. This approach not only shortens the lifespan of devices but also reshapes the consumer's relationship with technology, normalizing frequent replacement rather than long-term ownership. Furthermore, the durability of older technologies was connected to a slower pace of innovation. In the early and mid-20th century, products were not expected to be replaced annually or even every few years. A refrigerator purchased in the 1950s might remain functional for 40 years, and a rotary telephone could last even longer. Companies invested in building trust through longevity, and consumers, in turn, expected their purchases to serve them reliably for decades. Today, however, the rapid cycle of technological advancement has redefined expectations. Newer models of smartphones, laptops, and even cars are released every year, encouraging a culture of constant upgrading. The pressure to innovate has created a paradox in which devices are not allowed to reach their maximum potential lifespan before being rendered obsolete by social or technological forces. The psychological effect of this change cannot be ignored. When older generations recall the reliability of past technologies, they are not only remembering physical durability but also the sense of stability and predictability it provided. A refrigerator that never failed, a radio that worked reliably through blackouts, or a car that could be repaired with basic mechanical knowledge provided reassurance in everyday life. The breakdown of modern devices, which often occurs without warning and requires costly replacement, erodes consumer confidence. This shift in consumer psychology highlights that the durability of older technologies was not merely a technical achievement but also a social and cultural one. In addition, the environmental consequences of material durability versus disposability are profound. Older technologies, by virtue of lasting longer, reduced the frequency of waste generation and resource extraction. While they were often bulkier and less energy efficient in operation, their long lifespans minimized the overall environmental footprint. Modern devices, on the other hand, are lighter and more energy efficient but produce significantly more electronic waste due to short lifespans and the difficulty of recycling complex, multi-material products. This irony underscores a crucial lesson. Technological progress must consider not only immediate performance gains but also long-term sustainability. In conclusion, the durability and longevity of older technologies were not accidental byproducts of primitive design, but the result of deliberate material choices, cultural values, and economic incentives that favored permanence. By comparing these practices with today's emphasis on disposability and rapid innovation, we can see that better technology is not always synonymous with newer technology. The endurance of past devices demonstrates that longevity itself is a vital form of progress, one that may need to be rediscovered as societies confront the growing challenges of waste, sustainability, and consumer trust. 2. Planned obsolescence and economic incentives. One of the most profound reasons why older technologies often seem to outperform their modern counterparts lies not in the superiority of past engineering techniques but in the economic structures that shape design. The concept of planned obsolescence, the intentional design of products to have a limited lifespan, has become one of the most influential forces in modern consumer markets. While not always explicitly acknowledged, this practice ensures that products fail, become outdated, or lose efficiency within a predictable timeframe, compelling consumers to purchase replacements or upgrades. This cycle, while profitable for manufacturers, has fundamentally reshaped the relationship between people and technology, replacing durability with disposability and reliability with dependency on continual consumption. Historically, manufacturers often designed products with the expectation that they would last as long as possible, since their reputation depended on customer trust and word of mouth. A sewing machine or refrigerator built in the 1940s, for instance, was a reflection of a company's craftsmanship. Consumers were unlikely to buy another refrigerator for decades, meaning that brand loyalty had to be secured through reliability rather than rapid replacement. However, as mass production expanded in the mid-20th century, industrial leaders began to realize that longevity was economically disadvantageous. If every household purchased only 1 or 2 refrigerators in a lifetime, growth would stagnate. Thus, a gradual shift occurred, where the business model no longer revolved around creating the longest-lasting products, but rather around stimulating continuous demand. The most famous historical example of planned obsolescence is the Phoebus cartel of the 1920s and 1930s. This group of major light bulb manufacturers, including General Electric and Philips, secretly agreed to limit the lifespan of light bulbs to around 1,000 hours. Prior to this, bulbs were capable of lasting much longer, sometimes exceeding 2,500 hours or more. By deliberately reducing durability, the cartel ensured that consumers would have to repurchase bulbs more frequently, creating a steady and predictable stream of revenue. This case illustrates how technological capability was deliberately suppressed in favor of profit. The light bulb became not just a symbol of modernity but also an early victim of economic manipulation, and its story set the stage for a broader pattern across industries. Today, planned obsolescence manifests in far more sophisticated ways. Instead of simply making devices physically fragile, manufacturers often employ technological and software-based strategies to shorten effective lifespan. For example, smartphones are notorious for experiencing slowed performance or incompatibility with new operating systems after only a few years. While the hardware itself may remain functional, software updates are discontinued, or new applications require more advanced specifications, effectively rendering older devices obsolete. Printers, another common example, often use programmed page limits or ink cartridge chips that prevent usage beyond arbitrary thresholds. Even cars now incorporate complex electronic systems that can lock out owners from simple repairs, ensuring that maintenance and upgrades must be performed by authorized dealers at high cost. The psychological aspect of planned obsolescence also deserves attention. Modern consumers are conditioned to view constant upgrading as a normal part of life. Advertising plays a critical role, portraying the newest smartphone, car, or appliance as not only technologically superior but also socially essential. In this environment, obsolescence becomes both a technical and cultural phenomenon. Devices that still function may be discarded simply because they are no longer fashionable or compatible with the latest trends. This fusion of marketing with design strategy ensures that consumers willingly participate in the cycle of disposability, often without fully realizing that the system has been engineered to encourage it. In conclusion, planned obsolescence reveals a central paradox of modern technology. Advances in science and engineering have made it possible to build machines that could last longer than ever before. Yet economic structures actively prevent this potential from being realized. Where older technologies were constrained primarily by the limits of available materials and techniques, modern technologies are constrained by business models that prioritize profit over durability. The study of planned obsolescence not only explains why older technologies often seem more reliable but also challenges us to rethink what progress truly means. Should innovation be measured by speed and novelty, or by the ability to create lasting, trustworthy, and sustainable tools for human life? Until this question is resolved, the cycle of obsolescence will continue to dominate, shaping not just our devices but the very fabric of modern consumer culture. 3. Simplicity of design and functionality. When examining why many older technologies are often perceived as more reliable or durable than their modern equivalents, one cannot overlook the role of simplicity in design and functionality. The engineering philosophy of earlier centuries and decades often prioritized straightforward mechanisms, limited complexity, and user-centered practicality. Unlike contemporary technologies, which frequently embed layers of digital systems, microprocessors, and interdependent components, older designs were constructed with an ethos of mechanical clarity. Each part had a defined role, and most devices could be disassembled, repaired, and reassembled with relative ease by either the owner or a local craftsman. This fundamental simplicity is not merely a nostalgic observation. It represents a technical reality that greatly influenced both longevity and user trust. The simplicity of earlier machines often meant fewer points of failure. Consider the example of a manual typewriter versus a modern laptop. The typewriter, while mechanically intricate, functioned on purely physical principles: levers, springs, and ink ribbons. Breakdowns were rare, and when they did occur, the causes were usually straightforward. Perhaps a spring needed replacement, or a ribbon had worn out. In contrast, a laptop integrates mechanical, electrical, and digital systems, each of which is vulnerable to failure. A malfunctioning circuit, corrupted software, or failing battery can render the entire device inoperable, even if its core mechanical functions remain intact. Thus, the more interdependent the systems become, the more fragile the overall technology appears. Historically, this emphasis on simplicity was not merely accidental but deeply tied to social and cultural conditions. In rural and industrial societies of the 19th and early 20th centuries, access to specialized repair services was often limited. Farmers, factory workers, and householders required tools and machines that could be maintained with basic knowledge and readily available parts. A plow, a sewing machine, or even a household clock had to be resilient in both design and repairability. Manuals often included detailed instructions, not just for use but for repair, assuming that owners would take responsibility for upkeep. In modern consumer culture, by contrast, the expectation of self-repair has largely disappeared, replaced by reliance on specialized technicians or, more commonly, the outright replacement of defective products. The simplicity of older designs also translated into remarkable adaptability. Many tools and machines were designed with modularity in mind, allowing components to be replaced or upgraded as needed. This modularity, while primitive compared to today's standards, provided a kind of resilience absent in many modern devices. For example, a 19th-century wooden cart could be repaired with locally sourced wood, while the wheel axle might be reforged by a village blacksmith. This adaptability was directly connected to the physical environment and the availability of local resources. In contrast, modern automobiles or electronic devices often require proprietary parts, specialized tools, or manufacturer approval, which greatly limits user autonomy and increases dependency on centralized systems of production and service.